We live in a world that often feels driven by pure chance. From the flip of a coin to the fluctuations of the stock market, individual events can seem utterly unpredictable. Yet, paradoxically, we routinely make astonishingly accurate statements about future events or vast populations. How can we possibly predict the unpredictable? The secret lies in a fascinating realm where randomness reveals its hidden patterns, the world of statistics. Think about a single coin toss. Will it land heads or tails? You genuinely can't know for sure. It's a 50-50 shot. But what if you tossed that coin 1,000 times? You'd be incredibly surprised if it landed heads every single time, wouldn't you? In fact, you'd expect something very close to 500 heads and 500 tails. This simple observation hints at a profound truth. While individual events are random, aggregate outcomes often follow predictable rules. This brings us to our first fundamental concept, probability. At its core, probability is simply the measure of the likelihood of an event occurring. It quantifies uncertainty on a scale from 0, meaning impossible, to 1, meaning certain. A coin toss has a probability of 0.5 for heads. Understanding these basic probabilities allows us to begin quantifying the world around us, moving beyond mere guesses. Once we start collecting data, we need ways to summarize it. Our first tool for this is the mean, often called the average. You likely encounter it constantly: the average temperature, the average test score, the average income. To calculate it, you simply sum all your values and divide by the number of values. The mean gives us a central point, a single number that represents the typical value within a dataset. However, the mean isn't always the full story. Imagine a street where 9 houses are worth $200,000, and 1 mansion is worth $10 million. The mean house price would be over $1.1 million, which is misleading for most residents. This is where the median comes in. The median is the middle value when all your data points are arranged in order. In our housing example, the median would be $200,000, a much more representative figure. Knowing the average tells us where the center of our data lies, but it doesn't tell us how spread out that data is. Consider 2 groups of students, both with an average test score of 75. In one group, everyone scored between 70 and 80. In the other, scores ranged from 10 to 100. The average is the same, but the consistency is vastly different. This spread is measured by concepts like variance and its square root, standard deviation. Variance quantifies how far each number in the set is from the mean. A high variance means data points are widely spread out, while a low variance means they tend to be close to the mean. Why does this matter? Imagine investing. 2 stocks might have the same average return, but one with higher variance is far more volatile and therefore riskier. Understanding spread helps us assess risk and reliability. As we collect more data, we often see patterns emerge when we visualize it. These patterns are called distributions. A distribution shows us the frequency of different values within our dataset. Some data might be skewed, with a long tail to one side, like income. Others might be more symmetric, with values clustered around the center. Perhaps the most famous and incredibly useful distribution is the normal distribution, often called the bell curve. You see it everywhere in nature and human endeavor: heights of adults, measurement errors, even the scores on standardized tests. It's symmetrical, with the majority of data points clustered around the mean, and fewer observations further away. Its predictability makes it a cornerstone of statistical inference. Now for one of the most powerful ideas in statistics: the central limit theorem. This theorem states that if you take sufficiently large random samples from any population, the distribution of the sample means will be approximately normal, regardless of the shape of the original population distribution. This is profound because it means we don't need to know everything about an entire population to make accurate inferences about it. The central limit theorem is the engine behind much of our ability to predict. Think about political polling. Pollsters don't interview every single voter, they take a sample. Thanks to the central limit theorem, even if voter preferences aren't perfectly normally distributed, the average preference from many large samples will form a normal distribution, allowing pollsters to estimate the true population preference with remarkable accuracy. This leads us to confidence intervals. Because we're working with samples and not entire populations, there's always a degree of uncertainty. A confidence interval provides a range of values within which we are confident the true population parameter lies, usually with a specified percentage, like 95%. It's how we quantify the wiggle room around our estimates, acknowledging that while we can predict, it's rarely with absolute certainty. These statistical concepts, probability, mean, median, variance, and distributions, culminating in the central limit theorem and confidence intervals, empower us to move from simply observing the world to truly understanding it. They transform raw, chaotic data into actionable insights, allowing businesses to predict consumer behavior, scientists to draw conclusions from experiments, and governments to make informed policy decisions. So, the paradox of chance isn't really a paradox at all. While individual events may remain fundamentally unpredictable, the collective behavior of large numbers, viewed through the lens of statistics, reveals profound and predictable patterns. By demystifying these core concepts, we gain the ability to quantify uncertainty, make surprisingly accurate statements about the future, and ultimately, navigate a complex world with greater confidence and precision.